This call is now being recorded.
Please excuse me. I will answer your questions after the presentation, and I am here as long as your questions and my knowledge lasts. So let's start with the design considerations of a heater. Uh, what is the criteria, and what the criteria is, and what is the philosophy for this designing of the heaters, different section, different parts of the different components of the heater, and also first from process point of view, and then after that from mechanical and structural point of view. So uh, let's go to our presentation. First of all, uh, uh, the theory for designing a fired heater uh, starts with a simple heat balance inside the radiant sections. The heat in the radiant section is supplied by three sources. The first one is the net heat of combustion, as I show it here. This is the net heat of combustion as denoted by Qn. The sensible heat of combustion of combustion air, which is injected inside the heater, and the sensible heat of fuel, which is injected inside the heater. Usually, these sensible heats show themselves in forms of preheating of air or preheating of fuel, or both together at the same time. And also, the heat is removed in three ways. The first way, the produced heat is absorbed by the tubes, which is shown here by QR. Some of the heat that is produced inside the uh, radiant section is lost through the valves refractory that are denoted by QL, the losses. And also, some of the heat inside this radiant section it goes into convection section, as it is denoted by QS. So we can say that by a simple balance of heat inside the radiant section, we have three heats that is the input heat, and we have three heats that is the output heat. The great thing that the scientists did was to calculate different terms of this equation, which I do not intend to go through this. It needs something about 15 to 20 hours to discuss how they reached, how they were able to solve the radiation problems inside the heater. I will introduce you a very good paper on how the formulation and the theory is developed inside the radiant section and the convection section. For now, just that we have a simple heat balance both inside the radiant section, also in the convection section. We have the same theory. Okay, move on to the next slide. Is the question that Mr. Kuhi asked, that how much heat is absorbed inside the radiant section, and how much of the duty is absorbed inside the convection section. You see that the percentage is 60 to 70% inside the radiant section, and 30 to 40% inside the convection section. You can change these numbers by playing with the geometry, with the number of tubes, with the distance of the tubes. All in all, you can change these numbers, but the thing that changes at the end is the efficiency of the heater, and many engineers worked on that and reached to the conclusion that if you keep these numbers, you will be as close as possible to the highest efficiency possible inside the heater. So, for example, if you see a heater, if you see a thermal calculation report which indicates that the duty inside the radiant section is, for example, 20%, and 80% is in the convection section, this is this is obvious that it is totally wrong. So keep in mind that the design must be something around these numbers, and the job of a good designer is to find the optimum uh, duty fraction inside the radiant and convection section. Okay, moving on. Let me talk a little bit about fluxes inside the tubes. First of all, what is a flux? It is the amount of heat per unit of time per unit of surface. This is the concept of flux. In other words, you can say that the unit of heat on the heat on the unit of time is power, and we can say it in other words, it is power on unit of surface. Uh, we cannot uh, put or emit as much as heat we want to a tube. We have limitations. We cannot say that we have, for example, 100,000 BTU per hour per square foot of flux on a hydrocarbon tube. A lot of things happen. First of all, the tubes are not able to withstand that much flux. So you will face metallurgical problems. And the second important issue is that you have process considerations. For example, if you have a stream of hydrocarbon inside a tube, hydrocarbons, especially higher hydrocarbons, are very prone to coking. So you cannot, for example, emit 20,000 BTU per hour per square foot of heat on a hydrocarbon stream, because it is decomposed and it is converted to coke, and it will in time it will reduce the heat transfer inside the inside the furnace. Also, for the matter of heat uniformity inside the furnace, you need to have a very uniform flux emitted on the tubes. The reason for that is in the formulations, in the development of the theory for the radiant section, as it is a thermodynamic and mechanics of fluids problem, there are some assumptions. One of the assumptions that is made through the theory is that the heat is distributed uniformly inside the heater, specifically in the radiant section. If you refer to API 560, the first paragraph of section 6 of API 560 indicates that the heater must be designed in a way that the heat shall be distributed uniformly inside the heater. This is because of the theory of the heater design. So I have brought a report of one of the refinery heaters I have designed recently. There is hydrocarbon inside the stream. I don't remember the composition very clearly, but you see that we have two definitions. We have average flux, we have peak flux. Average flux is the flux, is the power divided by the total surface of the tube. Peak flux is the power divided by the side of the tube, the surface of the side of the tube that is close to burner. It means half of the surface of the tubes. You see that the unit is BTU per hour per square foot, BTU per hour per square foot. You see that flux, this is radiant section, and up above we go to convection section. You see that I have kept the average flux something around 7,000, 8,000. This 13,000 is a little bit high. The limitation for this process is 12,000 based on the data sheets or project specifications by the client. So they are mostly uniform, and the flux is very, very well distributed. Uh, Peak flux uh, uh, are a coefficient of average flux, and they are a little bit higher. Uh, the permissible peak flux inside the heater totally depends on the geometry of the heater. Uh, for different geometries, you can check client specifications for the permissible heat flux and average flux. So you can find this flux in thermal reports of the heater design softwares. This is the report from FRNC software. HDRI software has also the same report available. Okay, let's go to next part, which is the convection section. Um, if you enter a fluid inside in the convection section, and this fluid passes through all the tubes, and then at the end gets out in from one of the tubes, you probably will have a lot of pressure drops. Uh, Normally, one of the limitations imposed on the heater designer is the maximum pressure drop. So one of the ways, uh, which is very normal in different heat exchanger designs, one of the ways to reduce this type of pressure, this pressure drops inside the heat exchanger or the heater, is to divide the fluid to, for example, 2, 4, 3, 6, 8 different passes, and reduce, see this equation, and reduce L, the length of the tubes that the fluid passes, and reducing this reduces the amount of pressure drop. This is the first way. This is the first thing that a heater designer must do after completing the thermal design. He needs to check for the hydraulic part of the design, to decide how many passes is needed to reduce the pressure drop. So for example, if I decide to divide the total flow rate to 4 passes, and also I have selected the nominal pipe size based on thermal design, I reduce the length, the length of the tube that the fluid passes. I reduce it and divide it by 4. So I shall have a 1/4 of pressure drop comparing to the previous condition. So we need to check the pressure drops, check it with permissible pressure drops after the thermal design is completed. There are very, very, very rare cases that increasing the tube passes doesn't solve your pressure drop problems. So you need to go back to thermal design and change the size of the tubes, which in these years of designing tubes, these years of designing heaters, has happened for me once. And the problem for me was that the heater was not sized properly at the beginning, that I faced this problem. In conclusion, if you have a properly designed heater, you won't you will solve the problem of hydraulic pressure drops by increasing the number of passes, and you won't need to change the nominal pipe size. Okay. Another issue that is important in hydraulic design is that you have to keep the flow regime inside the heater in certain regimes. For example, if you have only liquid inside the heater, it is obvious that you have to have turbulent flow regime. And why is that? Because the flow regime in turbulent mode the heat transfer is at its maximum. So you need to have turbulent flow. If you have two-phase flow inside the heater, you need to avoid a slug regime, because it has a lot of vibrations, and it causes problems with supporting, and it causes mechanical and structural problems. Uh, you can read a lot about slug regimes in piping publications, specifically in ASME publications, and you have to keep the regime of the fluid inside the pipes in plug or bubbly, are very good to keep the flow regime. There are a lot of publications on this in piping, because it is a major problem in piping design, and it directly affects the supporting design and stress analysis of the piping design. The same holds true for the heaters. Okay. Uh, I said that we need to have a uniform heat distribution uh, uh, inside the heater, and this is because the theory is developed with the assumption of a uniform heat distributions. To achieve this, we need to stick to certain ratios, certain geometrical ratios. For example, in paragraph 636 of API 560, you see that vertical cylindrical heaters shall be designed with a maximum height h to width ratio or diameter ratio of 3. It means that your heater cannot be very slim. And why does it say so? Because it contradicts the uniform heat distribution, and the equation of heat transfer changes drastically. So you have to keep a minimum. Also, we also have a criteria for single-fired box-type floor-fired heaters with sidewall tubes. We also have different height to width ratio at maximum and also at minimum for box-type heaters. You have to conform to them to have a uniform heat distribution. Okay. I talked about shield tubes. The picture on the right shows the burner looking above. You see that these are the radiant tubes. This is the crossover piping. What is the crossover? Crossover is the piping that connects the tubes in convection section to the radiation section. And also these white things are soft products of refractory. These are the radiant tubes. These are the convection section tubes, and of course, when you see above, first you see the shield tubes here. You see the shield or shock tubes here. They are not finned, and they follow the theory for radiant tube design. Also, as per API 560, shield section shall have at least 3 rows of bare tubes, which I already discussed the reason and the theory behind that. Okay. Suppose you have a heater. Uh, uh, what is the pressure of the flue gas inside the heater must be? Due to safety reasons, and also a little bit to heat transfer issues, you need to be slightly below the atmospheric pressure at the most positive section of the heater. In theory, it is proved that this section below the convection section, which is called the arc, has the most positive pressure inside the heater, the most positive negative pressure inside the heater. So if I keep this pressure, the flue gas here, if the pressure of flue gas here, I manage to keep it below the atmospheric pressure, I am sure that everywhere else, the pressure of the flue gas is definitely negative. So the pressure for the negativity of the flue gas criteria is here. You have to make sure that here it is the pressure of flue gas, is negative. This picture is taken from API 535 revision 2014. You see that uh, it mentions that you have to have uh, 0.05 or 2.1 inches of water gauges draft. Draft means negative pressure. So you have to have minus zero point 0.1 inches of water gauge of negative pressure here. This is the profile of the flue gas pressure change, draft change. See, this is the closest to this section is the closest to the atmospheric pressure, to zero pressure. So you have to keep that at the minimum safe distance to have a safe operating and an efficient operating heater. And the job of a good designer is to make sure that in all scenarios for the operation, for the startup, for the shutdown, we have this negative pressure below, just below the convection section in the arc. Okay. Now let's go to the mechanical consideration of the heater design. Okay. I will return to your questions. Just please let me finish the slides and we'll go through your questions. Uh, as I said earlier, we use refractories to use carbon steel material as the casing material. If I remember correctly, the minimum thickness that is allowed to be used in heater casing design is 6 millimeters. But it is obvious that this size of weights and loads cannot be borne by a 6 millimeters thickness plate. So it needs to be stiffened. The design of the casing is done by commercial finite element softwares, or also it can be designed by hand. And normally softwares, FEM softwares like StatPro is used, but you can use any other kind of FEM softwares like SAP, like SolidWorks, like ANSYS. All of them are possible. And a good question that may come to your mind, that is, how are the load combinations defined in designing the casing, the body of the heater? Load combinations are taken from building structural codes, which I introduce at the end of this presentation. Because it is atmospheric casing, it is not a pressure vessel. You can use load combinations addressed by building a structural code and use it to your benefit to design the casing of the heater. Radiant section, convection section, and stack. Also, we have a nominated code for the stack design, which I will introduce in the following slides, which is ASME STS1. Also, API 560 has an annex dedicated to a stack design. Okay. Now that we are able to structurally design the casing, we need to calculate the thickness of the tube that we need to use in different sections of the heater. API 530 helps us calculate the amount of thickness that is needed for the tube to withstand different kinds of loads. There are two criterion to design the tube per API 530. The first one is elastic design. The second one is creep rupture design. Both method thickness or thickness of the tube is calculated, and when compared together, And also, the creep rupture design is based on Larson-Miller parameter, and there are a lot of curves that help you use and define the Larson-Miller parameter based on the material and the temperature to select the correct thickness for the tubes of the radiant section and also the convection section. As I said earlier, this is possible to change the metallurgy of the tubes as the flue gas inside the convection goes up. Because the temperature decreases, you can reduce the metallurgy. It is possible to reduce the metallurgy and use a less strong tube inside the convection section. Many softwares help you calculate the thickness based on API 530. FRNC 5PC does that. HDRI does that. Also, I have developed Excel sheets for that, which is uses Larson-Miller parameter and elastic design method to calculate the thickness required for the tubes. These tubes that you calculated the thickness of them in the previous slides need to be supported. As I said earlier, the support design of the radiant section supports are not protected using refractory. So you need to choose the correct material based on table 11 in API 560, and they are catalog items, and you need to choose the material based on the temperature and order it to vendors that manufacture these supports. You see that this is a hanger that supports radiant tubes from above of the roof. These are spoon types. I have reduced its transparency. You see that? You see that these are the spoon types supports. That they are high alloys like STM A297, A30, A351, and A560, which you see that the material are 50 chrome, 50 nickel, niobium, or 25 chrome, 20 nickel, based on the temperature. I haven't seen any plates used as the form of manufacturing of the support. They are mostly casting, and they are carefully analyzed using finite element method and designed by the manufacturer. Okay. Now, another important topic that a manufacturer faces inside the convection section is the design of the tube sheets. See here, see the bottom right picture. These are called the tube sheets. The tube sheets that are between the two end tube sheets are called intermediate tube sheets. They are of high alloy material. They are manufactured using casting, and they need to be carefully analyzed, which the analysis is done as per ASME section 8 division 2, and it is very, very important to analyze these tube sheets correctly, and also you see that they need to be somehow connected using brackets. They need to be connected to the casing of the convection section. Also, the connection to the casing of the convection section are very, very important, and requires very extensive knowledge of the work in high temperatures with the either finite element methods or hand calculation methods. So you see here, these are the anchors of refractory. This is the tube sheet. Also, I would like to point out that these tube sheets has different geometries based on the design of different vendors. So you see that here this is a 2D tube sheet. You see that here this is a 3D tube sheet, and the geometries are quite different. Okay. And now, and finally, the importance of stack design. Uh, if you have used the commercial softwares like PV Elite, uh, you have probably seen the usage of ASME STS1 as the design method for stacks. API 560 in Annex H recognizes two types of methodologies for stack design. First of all, the first, I have brought them exactly from the Annex H of API. The first is the API method, which is based on an allowable stress approach for stability and vulnerability to wind-induced vibration, and is determined by limiting the stack's critical wind velocity within a specified range. This is the first method. The second method is the ISO method, which is based on the limit state principles from two certain Eurocodes and SysIn model for the steel chimneys. It is also analogous to the method given in ASME STS1. The stability is based on critical buckling strength and the susceptibility to wind-induced vibrations. So both of these methods, ASME STS1 and API method, have worked for me. I have designed them without problem, and the consultant and clients have agreed upon that. But I wanted to talk about these helical strakes. As you probably know, these strakes do not contribute to the mechanical strength of the stacks. They are used to break the wind-induced vortexes known as von Karman vortexes. These vortexes of vibration caused by winds produce a lot of pressure on the stack. So as ASME STS1 has indicated, you need to at least use these helical strakes on the 1/3 of the above height of the stacks, so that you won't face your stack won't face the pressure caused by von Karman eddies. That is very dangerous for the failure of the stacks. Okay, and the last part, as I call it, a work of art. I don't want to talk about the process and thermal process of designing and choosing refractory layers inside the vessel. You see that I brought the upper right picture. You need to have the amount of loss, which is limited by API 560. You have to have the amount of loss the amount of heat that is going to exit from refractory, after that from the vessel shell, and then out, to determine this temperature and define the thickness required for the refractory. This is the obvious process of designing and choosing for thickness of refractories. I wanted to point out the mechanical part of designing refractories. You have to be aware of a few things. Refractories should be designed in a way that you have the hot face always in compression. So if you choose the thickness of the refractory, the hot face may go into tension. So you need to increase it to go to make the hot phase experience compression, because the cracks that are initiated during cool down should be sealed up in normal operation and during the startup. So I wanted to mention that defining the thickness of a refractory is not only the job of the process department. Uh, the mechanical department needs to check the thicknesses and to confirm that each layer of refractory selected for the vessel does not fail mechanically, both in compression and tension. And uh, 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 we have to make sure that the uh, hot phase in the operation remains in compression. And also we have to note that we cannot increase the thickness to increase the compression on hot phase. Excessive compression on the hot phase will cause spalling, which is one of the failure methods for refractory. So uh, uh, I think it is very important to have a very deep understanding of mechanics of materials for the mechanical design of the refractories. See, that is a finite element analysis of the uh, uh, 1, 2, 3 layers of refractory. See, these are 3 layers of brick, and uh, they are uh, they are separated by mortars, and they need to be analyzed correctly to avoid excessive compression and tension. And with this slide, my presentation on refractory on design inside finishes, and I would like to introduce some good reads on different areas of the heaters. If you want to have a good grasp of thermohydraulic design, uh, these two very famous books are good reads. Also, this paper, Rating Fired Heaters from 1963, written by Dr. Wimpress, uh, is very eye-opening and helps you a lot in designing heaters. Also, on structural design, load combinations, methods of analysis, you can use structural codes, ASC 7, and also code of standard practice for steel buildings and bridges. These two in combination can help you design and analyze the casing of the radiant section, convection section, and the stack, also the stack. Also, if you are interested in the process design and how to control that process, there are 2 very good books, Piping and Instrumentation Diagram Development by Mr. Moto Brai. Uh, Unfortunately, he is not currently in Iran, but the book is gorgeous, and for any process engineer, I think it's a must read. And also, one of the hardest books I've ever read is the Process Control. It's a very big book by Dr. Marlin, and it has a lot of good insights on how to control heaters, different heaters in different scenarios. Also, if you want to understand refractories deep from a material point of view, I solely recommend these 3 very good books. And they are very professionally written. And for example, in the first one, the know-how for making different sort of types of refractories is also addressed. Also, if you want to know more about industrial burners, uh, this is Mr. Bokal, if I pronounce his name correctly, uh, is is the master of combustion and burners, and this is a very great book and also a big book. And also, let's not forget that we are playing mostly uh, in the field of API standards, which are which have limited us and helped us and guided us through heater design. First and the most important is API 560 for the heater itself, API 530 for the thickness calculation of heater tubes, 535 for burners. But remember that these burners are for, I think as I remember correctly, uh, they are gas-fired burners. They are not applicable for liquid fuel burners. And also one of the most important and yet not very paid attention to standards is API 556, which addresses the different uh, instrumentation and control and protective systems that is required for a successful design of a heater. That's it. Thank you. Uh, I hope you are not tired and everything. You can contact me or my company from the contact points that I have written here. Uh, Thank you. Uh, uh, I am here if you have any further questions. Let me review the questions here. Okay. I'm here for a Q&A session. First of all, I start by answering uh, the questions written here. Mr. Jafari Gol said, "Why the coils are bended?" Uh, I don't remember where you mean the coils are bended. Uh, uh, please clarify which slide you meant or which heater configuration you meant. Mr. Darvish said, what are the key factors to consider during design and operation in reducing NOx and CO2 emissions? Okay, to reduce NOx emissions. First of all, you need to understand. You have a deep understanding of the mechanisms of NOx production inside a heater. Um, uh, I consider your fuel clean. You have no nitrogen-bound fuel. I consider it a natural gas burner heater. We have three different mechanisms of NOx production. The most important one and the most dominant one is the thermal NOx, which happens above the temperature of 1,100, and it increases exponentially with increasing the temperature. You need to keep the temperature of one of the ways to avoid the production of thermal NOx is that you need to keep the temperature of the burner low in order to reduce the NOx production. Also, there are different methods to, for example, you cannot keep the temperature low as per process requirements. There are different methods as the post-treatment of NOx reduction. One of them is SCR method, selective catalytic reduction. You pass the flue gas on a catalyst that absorbs NOx and changes, and a chemical reaction happens that NOx converts to N2 and H2O. Another method is SNCR, selective non-catalytic reduction. You spray ammonia or urea inside the flue gas, and it reacts in certain temperature range. It reacts with the NOx, and the NOx is reduced. Also for CO2 emissions, to keep the CO2 emissions low, you need to be sure that you have a complete combustion inside your heater. And also, if considering all the good performance of your heater, there are scrubbing methods to scrub the CO2 out of your flue gas. Another question is that using fan or blowers can help achieve this. Yes, it may reduce your emissions, but it will also reduce your thermal efficiency. Uh, fans need to be uh, fans need to be carefully placed and selected in order to achieve a good thermal efficiency. It is not it does not help. It does not reduce it, because yes, it does reduce it, but at the cost of reducing thermal efficiency, which is not favorable. Uh, I, I I hope I have answered you correctly and completely. Mr. Jafar Gold said that the excess air act like the dilution and reduce the percentage of NOx and CO2, and uh, does not help. In fact, uh, um, excess air, the relationship between excess air and CO2 and NOx emissions have diagrams. First of all, you need to make sure that your excess air is correct, that your combustion is complete. This is the priority to have, and the blowers are sized based on that this completeness of combustion. And the criteria for that is that you have to have 2 to 3% of moles, dry moles ppm, dry moles of oxygen inside your flue gas to be sure that you have a complete combustion. Uh, Mr. Jafar Gold again said refineries usually use this method to cheat the environmental rules during analyzing and passing the checklist. I don't remember which method you mentioned, but I would be glad if you clarified. Mr. Askari said increasing the tube passage would result in increasing the velocity in tubes. Yes, but if I was expecting someone to ask this question. Yes, it changes the velocity in tubes, but the increasing number of the passes, the effect of the reduction in L is so much higher that the pressure drop is met while you can be in the range of allowable velocity in the tube. So that's why you have a 1 meter per second to 3 meters per second velocity window, and increasing the number of passes should help you stay in that velocity range. This is my experience in designing. Mr. Raul said no, increasing the tube passes will lower velocity. Because yes, I have answered that question. Thank you for your answer. Uh, yes, thank you. Mr. Akbari said, I really thank you for this conceptual presentation. I'm very happy today because thank you, Mr. Akbari. The pleasure is all mine. I am very excited to have you here. Also, Mr. Ismail Zadeh, I'm very excited to have you here. It's my honor to talk with you here. Mr. Jafari Gold said, would you please share the book? Please tell me which book you mean. Sure. Email me or text me somewhere. I will send you the books you require. Mr. Jafari Gold again said it was for multiple passes bended. Yes, I remember the picture. See, the dimension of the heater imposes limitations that you need to have the fluid go and return. So we need to have return bends inside the heaters, both in convection section and in radiant section, if that was what you expected from me. Ms. Mona said, thank you for your willingness to share your professional knowledge. Thank you to you too. Okay, Mr. Ismail said, please describe the acid point and limiter. Yeah, okay. This is a very important question, that these stacks are designed based on acid point and limitations, acid dew points. See, you cannot extract a lot of energy from flue gas very much. And how much is the lower bound? it depends on the composition of flue gas. For example, if you burn natural gas, uh, you won't have any sort of gases that are able to produce acid with the humidity inside the air. For example, uh, if you burn natural gas and you don't have any other pollutants or contaminants, you can bring the temperature down up to, for example, 50 or 40 or 60 degrees Celsius. But, for example, there is a scenario that you have sulfur inside the fuel that you are burning. So when you burn it, you produce, for example, SO2. Uh, that when SO2 is inside the flue gas, it is very possible to react with the humidity inside the air at in at the sea level pressure in the temperature of 130 degrees Celsius. So you should not pass, you should not come below this temperature, because the SO2 will definitely react with the humidity and moisture inside the air. So for different types of pollutants and different acid making components, for example, SO2, Cl, chlorine, uh, uh, we need to check the composition of our flue gas, and we need to check their acid dew points. For example, you have SO2, and it is possible to make H2SO4 sulfuric acid below 130 degrees Celsius. So we need to keep the stack temperature 10 to 15 degrees above the acid dew point temperature. This is the limit. This is the lower bound limitation for reducing the temperature in the stack. Uh, for other acids, for HCl, hydrochloric acid, for HF, you need to check acid dew points in the temperature of the in the pressure of which heater is working. This is not only holds true for the heaters. It is also a major problems in steam reformers. It is also major problems in crackers. I am having problem right now in incinerators, which are very prone to this problem, because in incinerators you have streams that are very contaminated, and they are very dirty, and there is a possibility that you have a lot of pollution. So you need to check for acid dew points. 2 years ago, I went to a steel plant, a direct reduction iron plant, and their steam reformer stack was merely torn down because of the presence of sulfur, and they extracted a lot of energy from the flue gas in their recuperators, which is the equivalent for convection section, and the stack was all corroded and was not able to work correctly. So we need to check the acid dew points based on the composition of the flue gas. Mr. Askeri said the tubes are not welded to tube sheet and can move freely, as you said. Uh, would you please explain the reason? Yeah, the tubes that pass through the tube sheets, because they're experiencing a lot of high temperatures. For example, they go from ambient temperature to you suppose 800 degrees Celsius. They cannot be welded. The weld definitely cracks. And the support should support this, and they should move freely. And there are two forces. When they move freely, there are two forces acting on the tube. One, the weight of the tube downward, and one, as per API 560, and one, the friction that is caused by moving in the tube sheet, which is a static friction. As you remember your high school physics, it is a kinetic static. Sorry, it is static friction with the coefficient of static friction of 0.3. And this is the mechanical design criteria for the tubes and the tube sheets, because as per Newton's law, the the forces act on each other. Act third law of Newton. The forces act on tube and on the tube sheet, and these need to be considered while designing. Uh, Mr. Jafar, I guess it's preferred to choose forced mechanical drafts such as air coolers because of because of facing the motor to hot gas. The motor is not the motor does not experience the hot gas. The impeller and the ceilings uh, uh, experience the hot gas. Yeah, I mean what you mean in air coolers, but this does not happen. This is not the same because the flue gas doesn't pass above the electrical motor. It only passes from the fan. It might have a leak, but it passes the impeller, and the motor is not exposed to hot gas. Mr. Lowe said, thank you, Mr. Lowe. Just for information, please refer latest API standard 5 July 2024. Yes, thank you. I don't have the recent edition, but Mr. Raul, if you are available, you can check WRC. I don't remember the number, but the API 535. Sorry, you said 535. I said you said 530. Okay, thank you. I don't have the latest revision. I try to get it. Mr. Esmail, thank you. Excellent information. Thanks. Thank you you too. Mr. Ansari has thanks. Mr. Askari, Mehdi Tahir, thank you. Thank you so much for your wonderful presentation. Thank you all. I am again very proud that I had you in my presentation. Have a good night. I'm available via email, via LinkedIn, and my social media are available for you if you can contact me for further information. Thank you. Good night.
Uh, Dear Mr. Nash, sorry, do you hear me?
Yes, I hear you loud and clear, Mr.
Yeah,
Fassi.
I'm. First of all, I should thank for your valuable uh, uh, webinar. But I have another question about the criteria for the velocities of one of the attendees asked you. We
Okay.
have some design criteria about the acceptance criteria for the velocities in tubes in heat exchangers for some fluids and materials. But you answer me about the we have a design criteria for velocities from 1 meter per second through 3 meter per second. It is recommended in API or not? It's
Yes.
recommended in best practices.
Okay. Thank you for your question. That is an important question. First of all, we need to be careful that what is the regime of our flow and what is the phase of our flow inside the heater. Uh, uh, if you have I must tell you that there is no such a thing as a velocity criteria inside API that are mentioned inside in any standards. I haven't seen that. 1, 2, 3 is written in I guess UOP specification in one of the projects. I think, if I remember correctly, in PDH heaters, if I remember correctly. And 1 to 3 meters per second is it has been written in Iranian standards, NIOC, and we must be careful that these are based on project specification and may change project to project. And also the thing I said, that the criteria I said is only for liquid heaters. And of course, for two-phase flow, we have other things that the velocity of the fluid is different from the velocity of the gas inside the tube. So to answer you correctly, no, it is not written in API. It is per different specifications. And also, you noted an important point: the amount of permissible coking and also the amount of fouling and scaling on the tube, in foul is very similar to shell and tube heat exchanger for fouling inside the tube. So caulking and the project specifications must all together be considered to choose a correct velocity criteria inside the tube.
I really appreciate your answer, Mr. Nash.
Thank you.
Thank you. Bye.
Okay, good night. Have a good night. Thank you all.
You too. Bye.